Angile. How's it, Caden? I wonder where are all the other people that were here yesterday. I hope we can all come and rally along. Guys, today we are going to actually pick it up from where we left off yesterday. Yesterday with the grade 12s. Yeah, Caden. Yesterday with the grade 12s, we actually we started looking at functions. Yes, we did. And no, I'm good, Caden. I'm good. It's good seeing you. And we had looked at straight line functions. We looked at everything that has to do with the standard form, m the gradient, c the y-intercept, m how when the gradient is less than 0 the graph is decreasing, m greater than 0 the graph is increasing, m is equal to 0 the horizontal line that exists, and then when m is undefined the vertical line. When m is equal to 0, y is constant. When m is undefined, or when the gradient is undefined, then it is x that is constant. We looked at the concept of domain yesterday for straight lines, how x is an element of real numbers. If the straight line is obviously a decreasing, increasing horizontal line and it is unrestricted, okay, then obviously this applies. But then if it is restricted, then we look at how far it is restricted, okay. Then we looked at range. Obviously range means all possible y values where the function exists, whereas domain is all possible x values where the function exists. Then we looked at the standard way in which we find the equation of a straight line, and we looked at this formula form that is always available in our formula sheet. We then touched on some grade 12, the fact that if an equation of a straight line is y is equal to mx plus c, then the inverse of that function, we can find the equation of that straight line by ensuring that firstly we swap x and y. Alright, so if that's y, the y becomes x, and if that's x, the x becomes y. And then we make y the subject of the equation. How? We take the constant, we transpose it, and it becomes x minus c on the other side, and then we divide by the coefficient of y, which is m, and that is why you have y is equal to x over m minus c over m. So generally speaking, that would be the equation of the inverse of a function when we have a straight line. Then we looked at parabola as well, and we touched on parabola quite extensively yesterday. Alright, and guys, if you really want to check this out, all of it, what I did here, you are more than welcome to hop on to the YouTube channel and actually check out the video that I did, because I summarized the concepts that are important for parabola. We looked at the turning point form of the parabola function, how to get the equation of the axis of symmetry, okay, and then we looked at how to get the minimum value or the maximum value depending on whether a there is less than 0, where we know if a is less than 0 we have a sad face, so that means we have a maximum value that we can extract from the function. If a is greater than 0, then obviously that's a smiley face, concave up, so basically you have a minimum there. Okay, then we looked at domain, how to write down the domain, how to write down the range, and then also we looked at how do we find the axis of symmetry if the equation of the parabola is actually in this standard form. How do we find the x-coordinate of the turning point? By using the formula x is equal to minus b over 2a, which is an important formula that we need to know, this one. X is equal to minus b over 2a. Then this form, we know, we always use this form whenever we want to find the equation of a parabola and we are given two x-intercepts and one other point. Okay. So today we're going to pick up, guys, from hyperbola. Okay, this is specifically custom tailored to grade 11 and grade 12 functions. There's the grade, you can see, guys. Because why are we doing grade 12? It's because grade 12s are writing on the 30th of October. It is not too far away now. Their final exam are less than a little bit over a month away. Okay, yeah. Yeah, so let's look at these now. What is that, guys? Do you know what is that? What is that? So come on, what is that? Okay, so guys, this is the standard form of the hyperbola function. Y is equal to a over x plus p in the denominator plus 2. Alright, this is in the numerator, the plus 2. The x plus p is in the denominator, the a is in the numerator. So this is the standard form of a hyperbola function. Y is equal to a over x plus p, then the plus 2, which is a constant term there in the numerator. Now, from this standard form of a hyperbola, we know that we have what we call the vertical asymptote, which has the equation of x is equal to negative p. How did we get this? X is equal to negative p. We took the expression in the denominator, which is x plus p. We equate it to 0. Then we solve that expression having been equated to 0, which gives us x is equal to negative p. That then gives us what we call the vertical asymptote. This word asymptote, okay, speaks to what we refer to as a boundary line. A boundary line. A line where the function does not exist. A line where the function does not touch. A line where the function does not cross, or even the function does not even so that's asymptote. It's a vertical line where the function does not touch. Okay, it's a boundary line, meaning it's not a solid line, but it basically has spaces. Okay, It's a spaced out line. That's what we call the vertical asymptote. And the equation of this vertical asymptote is x is equal to negative p. Okay. Then we have a horizontal asymptote. The equation of the horizontal asymptote in this situation is y is equal to q. Right? Since it's a horizontal line, it has the equation y is equal to, this q value here indicates what the horizontal asymptote will be. So y is equal to q is basically the general equation of a horizontal asymptote. Okay, and then x is equal to negative p is the general equation of a vertical asymptote. Okay, yeah. So I don't know if any of you have any questions about the vertical asymptote and the horizontal asymptote and how we are able to get the equations of the two. Vertical asymptote, you just take the expression in the denominator, you equate it to 0, you solve for that equation. You'll get x is equal to whatever the inverse of this value is. By inverse, guys, we mean the opposite value of whatever this is. So if this was plus 2, then the equation of the asymptote is going to be x is equal to negative 2. If this was negative 3, then the equation of the vertical asymptote is going to be x is equal to positive 3. So the vertical asymptote is always the inverse of this particular value that is next to the x in the denominator. Okay, that's the vertical asymptote, and it is a vertical line where the function does not touch asymptote. Horizontal asymptote, it's always going to be y is equal to, what is it going to be equal to? It's always equal to whatever the q value is. That's the equation of the horizontal asymptote. It's a horizontal line where the function does not touch. Okay. Then let's move on to this window, this one. Okay, hopefully we understand this window. Any questions, guys, from this window? Okay, vertical asymptote and horizontal asymptote. Any questions at all? I welcome questions, guys. If you have any question, please ask. Don't be scared to ask me a question if you are not clear about something. Ask, ask, ask. Okay, so silence means you guys don't have any questions, you're clear. Okay, then let's move on to this window. This a here at the numerator, if this a value is less than 0, we say that the graph will be found on the second and the fourth quadrant. I repeat, if a, the numerator value, is less than 0, meaning it's negative, then the graph, when we sketch it, is going to be in the second and the fourth quadrant. That's when a is less than 0. But when a, meaning this value there, variable, is positive, meaning it's greater than 0, then the graph is on the first and the third quadrant. Okay. So if you think about it, what we are saying here, this is the Cartesian plane. Okay. The minute you sketch in, let's just say these are our asymptotes. Let's say this is the horizontal line and this is the asymptote y is equal to 2. I'm just making an example. Does it make sense that y is equal to 2 if you look at the Cartesian plane? Well, yes, of course. This is the y-axis, this is the x-axis. So if the horizontal asymptote is y is equal to 2, okay, let's just say for argument's sake, then let's say the vertical asymptote is x is equal to negative 2. Let's just say for argument's sake. Then guys, the asymptotes then give us an idea as to where the quadrants are. This here is a boundary, okay, where the graph will not touch, because the asymptotes form our boundaries, okay. So this would be the first quadrant here. Grade 11 and 12, Erica. Grade 11 and 12. So this here would be the first quadrant. Quadrant number 1. This here would be the second quadrant. Quadrant number 2. This here would be the third quadrant. Quadrant number 3. And then this here would be the fourth quadrant. Quadrant number 4. So this is first because this boundary and that boundary define the first quadrant, my first quadrant. Then the boundary line here, the asymptote here, and this asymptote here, this is my second quadrant. Then this is my third quadrant, and this is my fourth quadrant. I hope that makes sense, guys. So if a is greater than 0, we are saying that the function can be found in the first and the third quadrant. So then that means if I sketch my function, guys, you can expect to find the function sketched there. That's the first quadrant. And here, that is the third quadrant. Okay, I'm just showing you guys generally that when a is greater than 0, when this here is greater than 0, the graph is on the first and the third quadrant. How do we understand? How are we able to locate where the quadrants are? That depends on our asymptotes, our vertical and our horizontal asymptote. Okay, so you define your quadrants according to the asymptotes. That's when a is greater than 0. First and third. I just want to do the very same scenario here, an example. Let's just say this is our horizontal asymptote again. This is just an example, guys, okay? Then this, let's just say, is our vertical asymptote. And let's just say it is x is equal to 3. Okay, let's just say 1. Okay. Then let's say that in the situation a is less than 0. That means our function is found in the second and fourth quadrant. So that would mean, in other words, that our second and fourth quadrant, where is the first, second, and fourth? Second and fourth, guys, this is the first quadrant. This is the second quadrant. Remember, the boundary lines define where the quadrants are. So the first is here. The first is basically limited where these lines, the vertical asymptote and the horizontal asymptote, are actually defined. So there is the first, this is the second, this is the third, and this is the fourth quadrant. So if they are saying second and fourth, I can expect to see the function here. Okay. And guys, what you should notice here is that these functions don't touch the line here, the asymptotes. They come close to the line, but they never touch. And the arms here are just smooth curves. This arm as well, you know, it's a smooth curve towards this asymptote, but it never touches this asymptote. This is my second quadrant, my arm in the second quadrant for my hyperbola. Then my arm in the fourth quadrant. Okay, so I'm sure you guys can see this. All right, when a is greater than 0, function is found in the first and the third quadrant. Okay, These are my asymptotes. The asymptotes define the boundary lines where the quadrants are. My first quadrant, second quadrant, third quadrant, fourth quadrant. So since a is greater than 0, function found in the first and the third quadrant. But here, a is less than 0. These are my asymptotes, my boundary lines first, second, third, and fourth. So that means that my function will be found in the second quadrant and in the fourth quadrant. Okay. So I hope that is clear for us, guys. Okay, when it comes to the hyperbola. Okay, no problem. Let's move on. So I hope we now have an idea. Okay, just to recap again. Remember, I said the standard form of a hyperbola is y is equal to a into x plus p plus q. We know that there are two asymptotes. There's a horizontal asymptote. Horizontal asymptote is always indicated by the q value. So y is always equal to whatever that q value is. So if it's a negative number, we would say negative whatever. If it's a positive number, then it's y is equal to the positive whatever value that is there. Then the vertical asymptote, it's a vertical line. How do we get it? We always take the expression x plus p, whatever the expression is there, we equate it to 0. We solve for that expression. We get x is equal to negative p. That is basically the equation of the vertical asymptote, and it is a vertical line, whereas the horizontal asymptote is a horizontal line. I hope that makes sense, guys. Right? So this is really shouldn't be a problem for us. We should all be able to know how to get the asymptotes. So if ever they're asking you in a question, what is the equation of the asymptote, and you are given the actual equation of the hyperbola, we should be able to say y is equal to q is the horizontal asymptote, or y is equal to whatever the q value is there, and then the vertical asymptote is always the inverse of the numerical term for your expression in the denominator. So if it's plus p, then obviously the equation is x is equal to negative whatever the p value is if it's positive. But if it's x minus p, then obviously it will be x is equal to the positive p value. So that's basically very important to note. Okay. If a is greater than 0, graph is found in the first and second quadrant of the asymptotes, so first quadrant and third. But if a is less than 0, then the graph is found in the second and the fourth quadrant. Never touching the asymptotes, coming very close, because boundaries, guys, in life you need to have boundaries as well. There are places in life where you need to come very close, but you must never, ever touch. I can't repeat or emphasize that. You know, it's like if you don't have boundaries, if you don't have asymptotes, you will mess up your life and you will mess up your own identity. Okay, I'm sure you may have seen in the media currently, there's a lot of coverage in the media currently of teachers that are actually going beyond the boundaries that have been set within the school context. And what you are seeing is, you are seeing sort of like a pandemic of sexual misconduct that is being done by quite reputable teachers who are supposed to be worrying about the welfare of learners, but they are not. Why? Because they have basically gone beyond the disciplinary boundaries which they're supposed to have set. Learners are learners, and in order for there to be safety and for everyone in the classroom set up to maintain a good sense of identity and safety, there has to be boundaries. Once we go beyond those boundaries, we lose our sense of identity and we can sabotage our own personal lives and our own reputation. So it's the same in life, right? So if there's anything that your hyperbola function teaches you, is that it is important to have boundaries. Remember, if the hyperbola does not have these boundary lines, it loses its sense of identity as a hyperbola function. It ceases to become a hyperbola function. It becomes something else. So in the same vein, we need to maintain those boundaries. Okay, so that's just a lesson in why asymptotes are important for a hyperbola function. Okay, let's go now and just check. Let's go check here now. What about the domain and the range of a hyperbola function? Guys, straightforward, this one. When we write down the domain of a hyperbola function, remember, the word domain, what does it mean? It's the possible x values where our function exists. The possible x values where the function exists. So if you look at these two functions that I've drawn here, these hyperbolas, both of them, when we look at the domain, okay, we are looking from the left to the right. And what are we checking? We are checking from the left to the right, where does the function exist? So what you can see is that, look at this arm, for instance. It's gonna go on, this arm is gonna go on infinitely in this direction, never touching the asymptote, but going all the way in that direction. It's amazing that you can go on forever in this direction, but you will never touch that line. Okay, one would think that this line will eventually, this graph will eventually become tempted to touch that line, but it doesn't get tempted. Though close it is, it never gets, it doesn't find itself on the boundary or beyond the boundary. It's always within the boundary line. So what I'm saying by that is that from the left, we are coming all the way from negative infinity. Then what happens? It goes down. Does it touch this line? Never. What is this line? This is the vertical asymptote. So that's why when we write the domain, we say x is an element of real numbers. What does that mean? It means that this function will exist everywhere for every real number. But then we write an exception and we say x cannot be what? X cannot be what, guys? Look at this vertical asymptote. X can never be what? What is the one x value where this function can never exist? It is when x is equal to negative 2. So we say x can never be negative 2. So when we write the domain of our hyperbola, we do say that the function does exist everywhere from left to right. In other words, from negative infinity to positive infinity, the function does exist. But with the exception of one place, the function will never exist on the asymptote. X can never be negative 2. That is the domain of this function. We don't exist only here, but look, we exist everywhere after that, all the way to infinity, but never touching this boundary line. So basically, that's why we say the domain, generally speaking, is x is an element of R, but x cannot be the value of the vertical asymptote. So that's why you find this thing here, that x is an element of R, but x cannot be negative p. What does the negative p represent? It represents the value of the vertical asymptote, the equation x is equal to negative p. So we say x cannot be negative p. This here is important, to say x is an element of R. That shows that we are agreeing that the function does exist everywhere for x from the left to the right, but with one exception. X cannot be negative p. So here, for instance, we say x is an element of R, but for this function, x cannot be what? Negative 2. Let's come here. If we were to write down the domain for this function, you can see the function, there it is. Okay, so from left to right, this function is coming from infinity, negative infinity. It approaches this line, but never touches this line. We can see the asymptote of this line. But then the function continues. After the asymptote, it continues increasing, never touching that line, goes in an infinite direction. So when we write down the domain for this function, what do we say? We say x is an element of real numbers, but x cannot be what? x cannot be 1. Okay, I hope we are together. When we're writing down the domain of a hyperbola, we must consider the vertical asymptote. X cannot be the value of the vertical asymptote, as we have seen here as well. X is an element of R, but X cannot be negative 2. Okay. Siyamba sonke, guys. Are we together here? I almost feel like I'm speaking alone. Like, no one is commenting, no one is saying a word. I can see the likes and stuff, like the tapping on the screen. Really appreciate that, but I'm not so sure if people are with me as far as writing down the domain, or it's something we know and we feel like I'm wasting your time. Okay, let's move on to the next thing, the range. When we are writing down the range of a hyperbola, we say y is an element of R. Y cannot be Q. Y cannot be Q. We say y is an element of R. So in other words, the function for the for y, the y value, the function is possible everywhere from the bottom to the top. Because remember, when we're looking at range, we're not looking from left to right, but we're looking from the bottom to the top. That's range. Range, when you write down range, we are looking from the bottom to the top. Okay, from the bottom to the top, that is range. So if we look at this function again, from the bottom, the smallest y value, to the top, the biggest y value, where is this function existing? Look at it. From the bottom, it's going up, but then it's the boundary line, that is the y value that limits this function from being able to exist in this line, is y is equal to 2. But remember, after that, look at it, it takes on again and it goes up all the way. So what can we say is the range? Okay, when we are looking at the range, we are looking from the bottom to the top. Okay, so that's why I'm drawing this arrow, from the bottom to the top. So the range there is y is an element of real numbers. I think we can all agree that the function does exist everywhere from the bottom to the top. So we say y is an element of R. But then there's an exception. Where is the exception? Okay, y cannot be what? The horizontal asymptote. So y cannot be 2. Okay, y cannot be 2. I just want to put this line there because I want you to see that the range is y is an element of R, but y cannot be 2. In other words, y cannot be the horizontal asymptote. Let's look at this one as well. Okay, you can see, look at there's the function. It's going up. Limitation is this horizontal line, y is equal to 2, but then it picks up again. So when I write down the range again, I say y is an element of R, but this here is like saying but y cannot be 2. Okay, so that is my range. So surely in tests, guys, when they ask us to write down the range of the hyperbola, it should be straightforward. Writing down the range of the hyperbola. Now we should have no problem writing down the range of the hyperbola. Okay, moving along very swiftly. So domain and range we are covered with the hyperbola. Then we have something called the axis of symmetry for a hyperbola. The axis of what? Of symmetry. Okay. I see what is written here, but honestly I feel like this is the most easiest way. You see this part, this one? This helps me easily write down the equation of the axis of symmetry for my hyperbola. You see this x minus p, this bracket? You see? Alright, I'm just gonna show you something here. Y is equal to, so this is the axis of symmetry. Y is equal to So the axis of symmetry, guys, okay, there are two of them. We have two axes of symmetries for our hyperbola. Okay, there is the positive gradient axis of symmetry, and then there's the negative gradient axis of symmetry. And so generally, if let's say this is the equation that we have for our hyperbola, I just want to write down a equation of a hyperbola. You can see it, guys. Okay, can you see this equation of the hyperbola? I hope you can, and I hope it's clear for all of you. Well, let's say this is the equation. Okay, so I want you to see both of these. Okay, can you see them very well? I hope you can. The first general form of the equation of the axis of symmetry for a hyperbola, as you could see, all right, they give us basically these. I love these two. Y is equal to brackets x minus p close brackets plus q. Okay, so if we look at the positive gradient axis of symmetry, the gradient is always positive 1. The gradient will never be positive 2 or 3 or 4 or 5. It's always positive 1, guys. I'm gonna say always within the framework of the grade 12 syllabus, grade 11 and grade 12 syllabus. If you are doing caps, always the gradient is 1. For the negative gradient axis of symmetry, the gradient is always negative 1. So that's basically one thing down, because whenever we want the equation of any line that is straight, we need the gradient, right? Okay, and then if we can get a point, then that basically solidifies everything. So generally speaking, y is equal to x plus p plus q. I just want to say that this part represents the denominator expression. Okay, this part represents the denominator expression. This part represents the q value of the hyperbola. And it's as simple as that, guys. It really is as simple as that. This part represents the denominator expression of your hyperbola. This part represents the q value of your hyperbola. And then the gradient is situated outside the bracket. Just like that. Again, if we have the negative gradient axis of symmetry, same thing. What did I say? This here represents the denominator of your what? Of your hyperbola expression or your equation, and this here represents the q value of the hyperbola. So if you have these down, guys, then you should be fine. I'm going back to your notes. Okay, y is equal to, if you have your positive gradient axis of symmetry on the outside of this bracket, there's a positive 1 here. You can't see the positive 1, but we know it's there. Then we have the expression of the denominator, and then outside the bracket we have plus q, which is the q value of the hyperbola. If you have your negative gradient axis of symmetry, then this negative represents negative 1 because your gradient is negative. The expression inside the bracket is the one that is found in the denominator of the hyperbola, and then this q value is the q value of the hyperbola function itself. So let's go now to an example and see how do we write the equation of the axis of symmetry. Let's say they had said in a question, find the equation of the axis of symmetry of the hyperbola. Find the equations. Okay, and let's say they were referring to this particular function. How would we go about finding the equations of the axis of symmetry? So I'm going to come and use what I've just explained to you. This form. Okay, this form makes life very easy. So let's go. Let's first write down the positive gradient axis of symmetry and say y is equal to, we know we start with y is equal to, then let's open our brackets. We know here we are going to write down the gradient. We are going to write down the what? The gradient. And what did we say the gradient is always equal to outside the bracket? If we are looking at the positive gradient axis of symmetry, we said the gradient is always equal to positive 1, guys. So all we are going to do is we are going to write 1 on the outside of the bracket. Are we together so far? I think we are good, most. I think everything's going well. Then inside this bracket, where we are going to go? We are going to go to the denominator of the hyperbola function. What is the denominator? It is x plus 1. The binomial is x plus 1. So let's go here and write inside that bracket x plus 1. Where did I get this x plus 1? It is the denominator of the hyperbola function. Then after that bracket, we write the q value. Where is the q value coming from? The q value of the hyperbola. What is the q value of the hyperbola? Here it is. It is, the sign is positive. The number is 3. So we go and write plus 3. Done. Okay. And then what we do is we expand. Take the 1, distribute it inside the bracket. Take the 1, distribute it inside the bracket. What do brackets mean? Multiply. What's 1 times x? It is x. What's 1 times 1? It is positive 1. By doing that, I remove the bracket, and then the plus 3 we add. And then the final answer is what? X. What's the like terms? What's 1 plus 3? 1 plus 3 is equal to what? 4. So the equation of the hyperbola, the equation of the axis of symmetry of the hyperbola that has a what? A positive gradient is actually equal to y is equal to x plus 4. Okay, now we are done with the positive gradient axis of symmetry. Now let's go and find the negative gradient axis of symmetry. What are we going to do? Let's go and write the form of the axis of symmetry of our hyperbola. Y is equal to, so y is equal to, what do we write outside the bracket? We know we always have a bracket, but then we write down the gradient outside the bracket. Since we are going for the negative gradient axis of symmetry, what did we say the gradient is always equal to? It's always equal to negative 1. So we go and write negative 1 outside the bracket. Then inside the bracket, what do we write? Let's go and check what's the denominator. The denominator expression is x plus 1. So we go and write x plus 1. Then outside, we are going to go and write down the q value. What's the q value? It's plus 3. So we are going to write plus 3. Then after that, what do? We distribute. Take the negative 1, distribute it inside the bracket. What's negative 1 times x? It's negative x. What's negative 1 times positive 1? It is negative 1. Then the plus 3, we just add. Then after that, we add the like term. So we have negative x. What's minus 1 plus 3? That gives us a positive 2. So then the equation of the straight line is y is equal to negative x plus 2. This is the equation of the axis of symmetry that has a negative gradient. Okay. These are my axis of symmetry. Okay. How difficult was that, guys? Can we now comfortably say that we can find the equation of the axis of symmetry if we are given the function of the hyperbola? Okay. I hope you guys can. Can you guys help me now find the equations of the x of symmetry if my hyperbola function is equal to y is equal to negative 2 over x minus 1 plus 2? Yes, you can, Rotendo, you can try. Can you help me find now the equations? I want the equations of the axis of symmetry for when the hyperbola function is given as this. Okay, I showed you how to find the two equations of the axis of symmetry when the hyperbola function is that, but I want you guys to help me find the equations of the axis of symmetry for when the hyperbola function is y is equal to negative 2 over x minus 1 plus 2. Can you guys help me find the equations of the axis of symmetry? Okay, so I'm sure just one more time if I can repeat how I found the equation of this. Okay, how did I find the equations of the axis of symmetry for when the hyperbola function is that? Remember, I used the standard form of the, I looked at the form, remember, y is equal to, this is x minus p represented by what is in the denominator of my expression, then the plus q represented by the q value. Okay, yes, I want both the axis of symmetry, and then here my negative gradient axis of symmetry, so I want both of them. How do I find both the axis of symmetries for when the function of the hyperbola is that? Find the axis of symmetry, the equations of the axis of symmetry for this hyperbola function. That's what we want. Find the equations of the axis of symmetry for this hyperbola function. Okay, so hopefully we guys were able to do it very nicely and smoothly. Okay, finding the equation of the x of symmetry for y is equal to negative 2 over x minus 1 plus 2. So surely you guys saw that for your positive gradient x of symmetry, it's simply y is equal to, you have your 1 on the outside, then you have your bracket, which is obviously where you are going to drop the denominator of the hyperbola expression. What's the denominator of the hyperbola expression? It is x minus 1. So you drop that in here, and then the plus 2, you drop the constant term there, which is positive 2. You drop that down here. Okay. Then after that, what do? We distribute. So 1 times x, key x, 1 times negative 1 is negative 1. And then the positive 2, obviously, that features there. Then what do? You add the like terms. What do you mean by adding like terms? Negative 1 plus 2 we can add. So we get x is equal to plus 1. So we have y is equal to x plus 1, guys, which is the equation, the positive gradient. Positive gradient axis of symmetry. AOS means axis of symmetry. Then we go for the negative gradient x of symmetry. Negative gradient x of symmetry. So that is going to be y is equal to, once again, what did we say is the gradient of the negative gradient x of symmetry? We know that it's going to be negative 1 on the outside. We have the bracket. We are going to drop what inside this bracket? The denominator expression, which is x minus 1. Let's drop that in there. Okay. And then we write the q value. What's the q value in this case? It's positive 2. Then what do? We distribute. Negative 1 times x is negative x. Then negative 1 times negative 1. That's positive 1. We have the plus 2 there. Then we add the like terms. Negative x. What's 1 plus 2? That gives us 3. So y is equal to negative x plus 3. That is the equation of the gradient axis of symmetry that has a negative gradient. There it is. Okay, so hopefully you guys got these answers as well, and you can slowly but surely see that it is not something difficult to find the gradient, the equation of either the positive gradient axis of symmetry or the negative gradient axis of symmetry. And let us just look at how we represent this gradient when we draw a straight line. Guys, this straight line, when you do draw it, it is a straight line, guys, that actually passes through. Okay, like it passes through where the two asymptotes intersect. The point of intersection where these two asymptotes intersect is basically where this positive gradient x of symmetry will pass through. Also, the negative gradient x of symmetry will also pass through that same point of intersection where the asymptotes intersect. So that's just to give you an idea as to what do we mean. As you can see, this axis of symmetry, what does it do? It actually makes sure that our hyperbola is symmetrically, look at this, man. This line of symmetry, what does it do? It gives us a mirror image of the one arm on the one side and the one arm on the other side. Okay, that's what this positive gradient x of symmetry does. Look at this negative gradient x of symmetry. It does the same thing. Mirror image on this side, mirror image on that side. Okay, so that's why it's important, these positive gradient x of symmetry and this negative gradient axis of symmetry. Okay, and we need to just understand that it cuts through the point of intersection of these two axes of symmetry is actually where the two asymptotes intersect. Okay, and the coordinates of the point of intersection, look, the equation of the axis of symmetry, the equation of the asymptote is x is equal to 1. So that means the x coordinate will be 1, and then the y coordinate will be 2. Okay, because the point of intersection is actually where the x and the y value of the two lines meet. Okay, yeah. Okay, I hope that makes sense. It becomes very important in other circumstances. Okay, guys, I think we have basically exhausted concepts around the hyperbola. Now I'm going to turn our attention to the last function for today, which is an algebraic function, and that is our exponential function. Okay. The what function? The exponential function. The what function? The exponential function. The exponential function has the form y is equal to ab to the power x plus p plus 2. Y is equal to ab to the power x plus p plus 2. Okay. Where b is greater than 0 and b cannot be 1. Okay. There's only one asymptote here, and it is the horizontal asymptote. Y is equal to the q value. So basically this guy will give me the horizontal asymptote. Okay. Now with that said, 2 pins. When a is greater than 0, whilst at the same time b is greater than 1, we need to note a few things. When a is greater than 0 and b is greater than 1, this here means above the asymptote. In other words, the function will be found above the asymptote. As long as a is greater than 0, the function is found above the asymptote. But if a is greater than 0 and b is greater than 1, then we have an increasing function like that. The function is not a straight line. Okay, I'm just going to redraw this. Okay, I'm just going to remove that. If that is the asymptote, y is equal to 2, then this is how we would expect our function to be. Combination a greater than 0, that's obviously when the function is above the asymptote. We know this a is greater than 0 is specifically saying above the asymptote. You can see the function is above the asymptote. When a is greater than 0 and b is greater than 1, we know that the function is above the asymptote and it is increasing. It's going up, Moss. Okay, that's why we say increasing. As x increases, y is also increasing. Another situation when a is greater than 0 but b is between 0 and 1. Then once again, the function, since a is greater than 0, still means it's above the asymptote. Okay, function is still above the asymptote, but the only difference is that it is not increasing, but the function is what? It is decreasing. So y is equal to whatever that q value is. So if it's y is equal to 2, that's y is equal to 2, and the function is found above the asymptote. But it's not increasing, but decreasing. So in other words, if we're saying it's decreasing, it means it's going down. From left to right, the function is going down. Okay, y is equal to q would be the equation of the horizontal asymptote, whatever that q value is. If it's 2, it's 2. If it's 3, it's 3. If it's negative 5, y is equal to negative 5. Okay, yeah. that combination, a greater than 0 and b is between 0 and 1, in other words, b is greater than 0 but less than 1, then it's a decreasing function above the asymptote. A greater than 0 means above the asymptote. Let's look at this scenario. A less than 0. What does a less than 0 mean? Means below the asymptote. Below the asymptote. But what happens if a is less than 0 but b is greater than 1? Then what should we witness in our function? We witness a function that's like this. Okay. So in other words, this one is decreasing. Okay. We are below the asymptote, meaning y is equal to 2 is here, but then the function is found below the asymptote. If a is less than 0 but b is between 0 and 1, then our function is still below the asymptote, but it's not decreasing, but it is increasing. Okay. Okay, are we together here, guys? Okay, this is very important, because remember, once you have a solid conceptual understanding of this, then it becomes easier to answer questions related to the functions, because you know what to expect and anticipate. Okay, so the combination of a and b, if a is greater than 0, it means above the asymptote. If a is greater than 0, it means above the asymptote. But if it's a greater than 0 together with b greater than 1, we know we are above but increasing. If it's a greater than 0 but it's b being between 0 and 1, we know we are above but we are decreasing. If it's a less than 0 and b is greater than 1, we know a less than 0 means below the asymptote. So we are featuring below the asymptote, but we are what? Decreasing. So here b is greater than 1, we say increasing, but here when b is greater than 1, we say decreasing. You see? So it's almost as if this here conforms to what a kind of show us. We know that positive means sort of like increasing, if you want to call it that way, positive. So that's why if b is greater than 1, we are increasing, since a is greater than 0. But if b is greater than 1 but a is less than 0, we are decreasing. Okay, situated of course below the asymptote. So let's just always remember that. Combination, if a is less than 0, we know we are below the asymptote, but if we are between 0 and 1, it means we are increasing, right? Yeah, we are increasing. Whereas if a is greater than 0 and b is between 0 and 1, we are decreasing. Okay, so it's very important, that situation and that circumstance. So let's always know this. Okay, because if we know it and understand it, you can look at a function, look at the way it's drawn, and expect to know how it is going to turn out once you've drawn it. Okay, because you see, oh, a is like this, b is like this, so I'm expecting a drawing that is like this. Okay, yeah. Then, just one last thing, domain and range. Okay. Domain, remember, possible x values from left to right. If you look at this function, it's going to exist everywhere from left to right. There's no restrictions from left to right. This is going to go infinitely in that direction forever and ever, never touching this boundary line. And this one is going to go forever and ever in that direction, never ever stopping. So the domain is going to be x is an element of real numbers. As long as the function is unrestricted, we say x is an element of real numbers. Okay, this one, domain, again, domain for this function will also be x is an element of real numbers. In other words, the function exists everywhere from left to right. If it's unrestricted, then we say x is an element of real numbers. But if it was restricted, of course we would look at the endpoints and then write our domain according to the existing interval if they were endpoints. Maybe shaded, then we know we look at the x value here, we look at the x value here, then we look at where it exists between the two x values. But because this function is unrestricted, there's no end from left to right, it doesn't stop from left to right, we say the domain is x is an element of real numbers. We could also say, if we want, x is an element of negative infinity to what? To positive infinity, using open brackets, because x is an element of R means this as well. Okay, so it's up to you how you want to write it. You can write it like this, or you can write it like that. Those are both acceptable ways to write the answer. This one, from left to right, does the function exist? Yes. Again, the domain here, domain would be x is an element of real numbers. The function exists everywhere from left to right. And then here, what about this one? Does the function exist everywhere from left to right for this function? From left to right, I believe the function does exist. Everywhere. Okay, so you can say x is an element of real numbers as well there. Okay, so that's why in the notes they are saying the domain will be x is an element of real numbers. This is for unrestricted functions. That will always be the case. Then what about range? The possible y values where the function exists from the bottom to the top. Where does the function exist when the function is a greater than 0? We know that a greater than 0 means above the asymptote. So the function exists above the asymptote. So would we agree then that we can say y is greater than q? That's it. Y greater than q. If you write the range in interval notation, the function will not exist on the slide, so we don't say equal. We just say that the function exists above the line q. Not on the line, it exists above, because this function does not touch the line. That's a boundary line. It's a no-go zone area. Okay? Yeah, we don't touch, we don't cross the line. Okay, very important, guys, don't cross the line. If this exponential function crosses this line, it loses its identity. It loses its identity as an exponential function. It's no longer exponential, it becomes something else. So please make sure that that shows. So y is greater than q, that is the range. What about this one? We're still above the asymptote, so that would still be what? Range would be equal to y is greater than whatever the q value is. Okay. Or if you're someone else, you could say y is an element, open bracket, from q to infinity, open bracket. Okay. If you want to write it in interval notation, same thing here. You could say y is an element of q to infinity. Same thing. You could write that range in that form. Let's look at this one. This function is not existing above the asymptote, but since a is less than 0, the function exists below the asymptote. So from the bottom to the top, where? From the bottom to the top. We are not including that line, we are just below that line. So we can say for the range, y is less than q. Or if we don't want to write it in this form, we can say y is an element of, from where? From negative infinity, which is at the bottom, to where? To q, open brackets. You see? Okay. And I'm sure you understand that this same answer is going to apply here, because the function is also below the asymptote. So we can say y is less than q, or we can say y is an element from negative infinity to q. So you could say that as well. So it's up to you how you want to write the answer for the range. Okay. Hey, I hope we guys are getting this. Okay. So exponential functions are nice, because really and truly, for grade 11, this is basically the basic fundamental things you were supposed to have gotten and understood. Then of course in grade 12 you did the inverse of a exponential function. All of a sudden now in grade 12 you guys are told that if the function, for instance, is y is equal to 2a to the power x, if you want to write the inverse of this function, it is the log function. Okay, the inverse is the log function. Okay, so then what would you do if you are writing the log function? First and foremost, we swap around x is equal to 2 to the power y. That's where we would start. Then after that, what do we do? Then after that we say y is equal to, we make y the subject, then we say log what? Log x, which x? That x, and then the base is 2. Okay, so if you want to convert a exponential function to its inverse, then the inverse is the log form. Alright, so what you first have to do is you have to swap x and y. So that's why y is equal to 2 to the power x. What did you do first? We swapped it. In the place of y we write x, in the place of x we write y. Then after that we use the log form to convert our exponential to log form. Then it is y is the subject, 2 is currently the base of the exponent y, so it is log, the x on the other side, which is the subject, becomes log x, and then the base is 2, so it's log x base 2, and that is the inverse. So now we can say the inverse of the function is log x base 2, and that's how you get the convert the exponential function to a log form in grade 12, and that's what you guys did, the inverse function. Okay, and then of course the domain and the range. Of course guys, if we are saying that the domain and the range are a certain way, then it means that for the inverse, because we are swapping x and y, it means that the domain becomes the range and the range becomes the domain. Makes sense, right? So basically here, for instance, if we were to write this function and draw the inverse of this function, the inverse of this function would simply become, the domain would basically be the range. We would say x is less than q for the what? For the domain. And then for the range we'd say y is an element of real numbers, because we swap these around for the inverse function of this function. Okay, so yeah, that's something else that's sort of like important that we need to note. So what I've done, guys, is I've just summarized for you guys all 4 of the basic functions. Straight line, your linear function. I looked at the grade 11 concepts and the grade 10 concepts with the grade 9, and then looked at the grade 12, which is the inverse function, and the domain and the range. We looked at the parabola in the previous video, the previous live I did yesterday. We looked at the turning point form. We looked at the quadratic form. We looked at how to get the axis of symmetry in the turning point form together with the minimum and the maximum, looking at the condition of a, whether a is less than 0, where in that situation we have the maximum, or where a is greater than 0, in that situation where we have the minimum. And then we looked at domain and range. We looked at the quadratic form of the parabola function, how to find the axis of symmetry and the x-coordinate of the turning point. And then we looked at basically what we would use to get the equation of the quadratic function if we are given 2 x-intercepts and 1 other point. Then we looked at the inverse of the function for our parabola, And I basically did indicate yesterday that the inverse of a parabola in and of itself is not a function, but it is a relation. In order to write the parabola function, to express it as the inverse function, we need to restrict the domain of the original function so that the inverse can actually be represented as a function, 1 to 1. Then we looked at the hyperbola today extensively. We looked at writing down the vertical asymptote, the horizontal asymptote, how to be able to look at the graphical representation on the quadrants if a is less than 0 featuring in the second and fourth, a greater than 0 featuring in the first and the third, how to write down the domain and the range of the hyperbola function, and then how to actually write down the axis of symmetry simply from the equation of the hyperbola, taking the expression of the denominator, writing down the due value, and also indicating the positive 1 whenever we want the positive gradient axis of symmetry, writing down the negative gradient, writing down in the brackets the expression in the denominator for the hyperbola function, and then the due value as it appears in the actual function, and then basically representing the negative gradient axis of symmetry. We looked at that. Then we've just now completed how to look at the exponential function, the a and the b, what they mean, the q, what it means, and then basically how we can from there interpret certain things pertaining to the asymptotes, and also looking at the domain and the range and the inverse function according to the grade 12 syllabus. So that's in summary. I think now we are competent enough to actually come and look at questions related to these functions so that we can attempt exam type questions. So I think I'm going to spend the remainder of my life looking at these exam type questions, and then tomorrow we'll continue with the rest of the exam type questions. But let's look at some today. Guys, you can see here the sketch alongside shows the graph of f of x. F of x is equal to negative brackets x minus 2 the whole thing squared plus 9, and g of x is equal to b to the power x, where b is a constant, d is a turning point of f and a point of intersection of f and g. Okay, b is the y-intercept. Where's b? There's b. B is the y-intercept, and a and c the x-intercept. So a and c are the x-intercept. They're saying now determine the length of what? Of a and what? And c. Now a and c, we were told, are the x-intercepts of who? Of f. Here is f. This is the equation of f. So let's go find those x-intercepts, because to answer this question, the length of a and c, we need the x-intercepts. So where's the function? There it is, guys. It's f of x is equal to negative into x minus 2 the whole thing squared plus 9. And remember, when we want to find a, the x-intercepts, what do we do when we want to find the x-intercepts? X-intercept, we let what, guys? What do we let to find x-intercepts? We let y be equal to 0, right? Yeah, so we are going to come here. F of x means y. So let's rewrite this function. Y is equal to negative into x minus 2 the whole thing squared plus 9. Yeah. Now it makes sense. Substitute in the place of y 0. Alright, this kind of seems a bit more familiar. We take the 9 over divide both sides by a negative coefficient. This becomes positive 9. This becomes squared. You see, divide both sides by a negative because it's negative coefficient. Divide by negative, this side negative, divide by negative gives us a positive. But then what we do on the right, we must do on the left. So a negative 9 divided by negative 1 gives us a positive 9. Then of course, we do this. When we take the square root, guys, on both sides, remember, where the square is, we take the square root, but where there's a constant term, we take the square root and then we write plus minus. So that means plus minus 3 is equal to x minus 2. Now, two situations here, two answers. I'll get x minus 2 is equal to 3, or x minus 2 is equal to negative 3. These two answers of x is equal to 3, transpose the negative 2, or x is equal to negative 3, transpose the negative 2, I get x is equal to 5, or x is equal to negative 1. Now, I'm going to go back to my points. A is on the negative side of the x-axis. Remember, this is the y-axis, there's 0 there. My A is on the negative side. So A here is negative 1 and 0. Whereas C is located on my positive side of the x-axis. So that becomes what? Negative 1. No, sorry, positive 5 and 0. Okay, are we together here, guys? There. Okay, I just want to repeat what I did. I wrote down the equation of f of x. Since the function of f of x is the one that cuts through C and A, and I know the A is the x-intercept, I know that my x-intercept is where I let y be equal to 0. So I take the y, substitute in the place of y0. Remember, in functions, guys, f of x means y. F of x means y. So in the place of f of x, I write y, and then I substitute in the place of y my 0. Then I take this equation and solve it. Of course, I have used the form of taking the square root on either side after transposing that positive 9 and then dividing both sides by this negative coefficient of the x minus 2 the whole thing squared, and then getting basically the square root on both sides, plus minus, and then solving for x. Maybe someone else would have basically gone this direction. Let me just, because I need to be mindful of the fact that people don't think the same way. Someone else could have decided to do this, right? Open two brackets and then they FOIL. That would have been fine as well. So they say negative into, they have x squared, x times x is x squared, x times minus 2 is negative 2x, minus 2 times x is also negative 2x, and then negative 2 times negative 2 gives you positive 4, and then they write the plus 9 outside. I mean, that would have been also fine. Then you add the like terms inside the bracket. It's x squared minus 4x plus 4. Okay. Then they take the negative sign inside the bracket. Negative times x squared, negative x squared, negative times negative 4x plus 4x, negative times positive 4, negative 4 plus 9. Then they add the like terms that are there. Negative x squared plus 4x minus 4 plus 9 is plus 5. And since they see that the x squared has a negative coefficient, they divide by negative throughout, so that this becomes x squared minus 4x minus 5. Then they factorize. The factors of 5, which when I multiply give me negative 5, but when I add give me negative 4. factors of 5. Okay, very important. Remember, when I divide by a negative here, okay, I have a negative x squared plus 4 minus 4 plus 9 is plus 5. Then I divide everything because this is a negative coefficient. So I divide by negative 1. This becomes x squared. When I divide by negative 1, I divide this by negative 1. This becomes negative 4. I divide this by negative 1. This becomes negative 5. That's why you have this negative 5. Then we look for the factors of 5. Okay, but since the sign is negative for your constant, it means you won't have the same signs. You'll have different signs here. Okay, but the sign, the factor, the highest factor should have the negative sign. So we are going to say negative 5 plus 1. Okay, does that make sense? Yeah, guys, signs are important. I can't overemphasize. Then you say x minus 5 is equal to 0, or x plus 1 is equal to 0, because you have a product of factors equated to 0. So x minus 5 is equal to 0, x plus 1 is equal to 0. Okay, this was your standard form. These are your factors. You apply your 0 factor law, and then your roots. X is equal to 5, or x is equal to negative 1. So you can see that we got the same answer, x equal to 5, x equal to negative 1, x equal to 5, x equal to negative 1, with different approaches. So here our A, C. Okay, yeah, and then from there onwards, we want the length. Remember, they wanted us to find the length of AC. So AC, guys, is on a horizontal line. So we don't need to really use the distance formula. You can if you want, but I mean the A and the C are on a horizontal line. So when the points are on a horizontal line, or when, in other words, you have the same y coordinate, we can simply say AC is equal to x on the right. What's x on the right? It's the x coordinate of C minus x on the left, which is the x coordinate of A. What's the x coordinate of C? It's 5. There's a sign minus. Minus who? Minus 1. Remember, the x coordinate of A is negative 1. There's already a negative sign. So that means 5 minus minus is plus 1. So AC is equal to 6 what? 6 units. Okay. So we can use this formula for a horizontal line. How do you know a line is horizontal? It's when the y coordinates are the same for 2 points. Then you know that this is a horizontal line. And you can simply find the distance between those 2 points on a horizontal line by simply taking the x coordinate on the what? On the right, minus the x coordinate on the what? On the left. Okay, does that make sense, guys? What? Any questions? Any questions at all about this? Okay, this was a beautiful 4-mark question. Imagine, guys, 4 marks. Determine the length of AC. I repeat, the sketch alongside shows the graphs of f of x. Here is f of x. We are given the turning point form of f of x, and g of x, which is the exponential function, where b is a constant. Okay, b is a constant. D is a turning point of f. There is D. It's the turning point, we are told. And a point of intersection of what? Of f and g. Here, that's where this function and this function intersect. B is the y-intercept there of what? And A and C. A and C are the what? The x-intercepts of who? Of f. So that's why when we determine the length of AC, we wanted to first find the coordinates of A and C, because they are the x-intercepts of what? Of f. So we found the length of AC. How? By first finding the coordinates of A and C, by finding the x-intercepts. What does x-intercept for this parabola mean? It means we let y be equal to 0. So we did that. We let y be 0 in this function. We substitute in the place of f of x y, which is 0. Okay, because f of x is y. I did say f of x means y. So we substituted 0. Then we solved for x, guys. And it's very important, the skill of being able to either solve for x in this way that you see here, or if you don't want to, going ahead and expanding and solving for x in this way. At the end of the day, you get the same answer whether you solve for x on this way or you solve for x in that way. Okay, and then after you get your x values, your roots, your x-intercepts, you can write the points in coordinate form, right? And then you can go ahead and use the distance on a horizontal line. You always take x that's on the right, the x-coordinate of c, which is 5, minus the x-coordinate on the left, which is -1. You subtract those two. 5 plus 1 gives you 6 units, so that's the distance of AC. Okay. Any questions at all? I hope not. Let's go and look at the next question. Determine the value of B. For how many marks? For 2 marks. It's a level 2 question. For how many marks? For 2 marks. Determine the what? The value of who? Of B. Where is B? This B. B of the exponential function. Okay. And where is the exponential function? Here it is. Do we have a point that we know for sure, a coordinate lying on this line at all on this function? Any coordinate that we know? Well, you see D, we were told, is the what? D is a turning point of F and a point of intersection of F and G. Kamogelo, you're 100% positive. We have D. Zinzi, you are truly correct. We have D. What are the coordinates of D, guys? Okay, you should be able to look at this function and tell me what the coordinates of D are, because we can use those coordinates and substitute into the function and solve for B, can't we? So what are the coordinates of D? In the comment section, guys, please help me out. I believe in you. I trust in you. In you I trust. You guys are writing your finals in just paper 1. You'll be writing in not more than 30 days. Imagine you'll be sitting in the exam room on the 31st, yeah. Kamogelo, with a question mark. Do you need a question mark, Kamogelo? Are you not sure still? Kamogelo, you shouldn't be having a question mark. You should have a definite, for sure, you know what you're talking about. At this stage, we should be definite. Yabo? Yeah, flowers for laughs, eh? Flowers for laughs. Please, 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 be sure. Okay? Be sure, please. So yes, Kamogelo, Khoitsiona, and Kosindi Pile. You guys are 100% correct. The turning point, the inverse of the -2, which is +2, is the x-coordinate of the turning point, and the q value, +9, as it is the y-coordinate of the turning point. So you guys are 100%. D is equal to 2 and 9. So we are going to use that in the function. Which function? This one, g of x. G of x is equal to b to the power x. Since this point lies on this function, we are going to substitute it. Take the x, substitute it there. Take the y, substitute it there, because g of x means y. So we say 9 is equal to b to the power 2. Then what do? We solve for b. So b squared raised to the power half, the reciprocal, that's b. 3 squared to the power half, that's 3. Therefore, b is equal to 3. Are we expecting a positive b value? Definitely we are. Okay, not a negative b value. We're expecting a positive b value, because remember, there were restrictive measures put on the value of b. We were told that the value of b, if you can remember from the notes, b is greater than 0 and b cannot be 1. So b has to be more than 0. It can never be negative. So b is equal to 3 is valid. All right. Okay. Do we all agree? Okay. Because of the restrictive nature. Is it Kebusan? Hey, Kebusan wants to join my live. Is Mr. Top-Notch Genius here in the live. KB. I wonder what did KB get in the trial exams this time around. Did you were able to get 100% total for paper 1 and paper 2, Kebusan? That's if you can. Okay, Gamukhelo, we agree. Thank you so much. Let's move on to the next question then, guys. I think we're clear there. 1.1.3. Determine the value of x for which g of x is greater than or equal to 9. Determine the value of x for which g of x is greater than or equal to 9. For 1 mark, guys, g of x greater than or equal to 9. The value of x for which g of x greater than or equal to 9. Let's just try and make sense first of the question. Remember, with the 2 functions drawn, I'm just going to do my rough sketch here so that I can leave my virgin sketch there sort of like untouched, if you will, if you want. Okay. So let's be clear about this, that remember the coordinates of D, as you guys indicated, are 2 and 9, right? So that means when x is equal to 2, the y value there at this point is 9, right? Okay. So I hope you understand, guys. When the x value is 2, the corresponding y value is 9, right? I hope that makes sense to you guys. Now they are asking us for which values of x, determine the value of x for which what? G of x is going to be greater than or equal to 9. Determine the value of x for which g of x. Now g of x is which function? Which function are they talking about when they're saying g of x? They are talking about the exponential function. Okay, so if we go to the exponential function, here is the exponential function. We know that this d, where y is equal to 9 as well, is a point where this particular exponential function also passes through. So they are asking us which value of x shows us the function being what? Being above, greater than or equal to 9. In other words, being above or equal. That means on. Where do we see which value of x shows us this function being above the value of 9, but also being on the value of 9? Where do we see this function, this one, being on 9? So it is on 9 where x is equal to 2. I hope we can see that. When x is equal to 2, the value, the function has a y value of 9, which means it is equal, it is on 9. So where is it on 9? It's when x is equal to 2. Where is it above? Where is the function above 9? If we move slightly to the right of positive 2, then you can see the function leaves positive 9 and it goes above the value of 9. Here we know it's above 9 point something. We are going up, we are going further up, which means 10, 11, we can go further up and up. Okay, so we can all agree that when the function is, when x is greater than or equal to 2, that is when g of x is what? Is above 9. When it's greater than 2, when x is greater than 2, it's above 9. Meaning it's greater than 9. But when it is equal, when x is equal to 2, it is on, meaning it is equal to 9. G is equal, it's exactly equal to 9. when x is equal to 2. But when x is greater than 2, then the function is above 9. Do you see that, guys? So our answer is this. 1.3, it's when x is greater than or equal to 2. Yes, Kamukhelo, you could say, I love Kamukhelo's answer. You could also write your answer as x is an element of 2, included bracket, to infinity. Okay. All right. Yes, I will touch on trigonometric functions, but not today. Today I'm just doing algebraic functions. I hope you understand. I think maybe my next live lesson will be on trig functions, so that we can just sort of like do functions and complete it. So what I'm saying, but not necessarily tomorrow or the day after tomorrow, but what I'm saying is that at some point when I'm done with functions, I will do trig functions. Okay, so thanks for the question. I know some of you do struggle with trig functions, but understand that some of your struggles with trig functions lies with your lack of understanding with some concepts that are in algebraic functions. So for instance, this question that we have just been asked, this one, it's amazing how many learners would probably lose the 1 mark. You saw, for instance, I saw Khoitziona saying x is greater than 2. Now imagine if Khoitziona says x is greater than 2 alone. It means he is not accommodating equal to 9. Khoitzion is only accommodating greater than 9, meaning above the 9. Yes, the function g of x is above 9 when x is greater than 2. But what Khoitzion is missing out on is indicating where is the function g of x equal to 9. It is equal to 9 when x is equal to 2. So we must also factor that in. If the answer is x is greater than 2, it's incomplete. But if you say x is greater than or equal to 2, then it means you are accommodating both above 9, where the function g of x is above 9. That's what the greater than means. Where is the function above 9? And where is the function equal or on 9? So where is it equal or on 9? Is when x is equal to 2. Where is the function above 9? It's when x is greater than 2. So we are accommodating both, and the answer is correct when x is greater than or equal to 2. Or to write the answer differently, as Kamukhelo has said, we could say x is an element of, we include 2 to what? To infinity, open brackets. Very good, Kamukhelo. Very proud of you. Okay, very nice. Alright, let's move, guys. Let's move. These are nice questions, aren't they? Let's look at this one now. Write down the equation of who? Of h. Hypo. H. Where's h coming from now? We had no h function here. We had f and g. So that means h is a new function. Now what are they saying? They are saying write down the equation of h if h of x is equal to, so the way we form h of x is we take the function of f, all right, and then that means in the place where x would be, we are going to say x plus 2, and then outside of that we are going to subtract 9. Let us be practical about this. When we are saying plus 2, what are we actually saying? We are saying we are shifting this function. Plus 2 means to the left by 2 units. Right? We are shifting the function to the left by 2 units. And then what does this minus 9 outside the bracket mean? It means we are moving the function down by 9 units. You see? So this is plus 2 to the left, minus 9 down. Remember? Hey guys, very key this thing. So now we are going to play some algebraic games. Level 3 question, Suga. Even though it's level 3, but it's nice. We're gonna play some algebraic games. So that means f. Where's f? There's f. That means inside that bracket where x is, we are going to substitute x plus 2. Let's go. H of x is equal to f of x plus 2 minus 9. Let's go to that f. That f of x function, here it is. It's negative into Now in that place of x, we are going to say x plus 2. But remember, we are placing in the place of x the x plus 2. Then after that x plus 2, we are followed by what? By minus 2. You see? I hope that makes sense, guys. But then there's a square, so we must make sure we write the square. Then outside that bracket, what's happening outside that bracket? Outside the bracket, there is plus 9. Then we need to subtract 9 on the outside as well. You see? Make sense? Yeah, I hope it makes sense, guys. Inside the bracket, the x, we say x plus 2 in the place of x. We are replacing x plus 2 in the place of x. We're writing x plus 2 in the place of that x in its entirety. But then there was a minus 2 there, so we write that minus 2, the whole thing squared. Then outside, we are saying plus 9, but then we have to subtract 9, so there we subtract 9. Then now let's maneuver minus x plus 2 minus 2. That leaves us with x. Plus 9 minus 9, that leaves us with 0. So our final answer is actually minus x squared. That is h of x. H of x is equal to negative x squared. There it is. There it is. That is the equation of the function h of x. Okay. Did we see it in the same way, guys? Are we all perceiving things in the same way, or is someone crying somewhere? Write down the equation of h if h of x is equal to f into x plus 2. You will remember, guys, that usually in this place, there's usually, if there was just f of x, that would be simply talking about the function, all of it in its entirety. But they are saying f of x plus 2. That means we replace that x of ours, the little x that's there, we replace it with x plus 2. So that means in the place of x, we are going to write x plus 2. That's why I wrote x plus 2 minus. We follow it up with the minus 2 that was there. There's the minus 2 that was there. We follow it up with the square. There is the square. Then obviously we follow it up with the plus 9. There is the plus 9. But remember, in the formulation of h of x, there was a minus 9 outside. That means outside we subtract that 9 as they asked. Then we deal with the addition and subtraction of like terms and simplify. X plus 2 minus 2, 2 minus 2 is 0. We are left with x alone, which means we're going to square it. Plus 9 minus 9 gives us 0 on the outside, which means we just have 0 on the outside. Then minus into x squared gives us minus x squared. That is the equation of h of x. Done, done, done. Are we good so far, guys? Are we surviving? Are we surviving? Let me just check if everyone is still breathing. Kamokhelo is saying we are together. I love it. I love it. I love it. I nearly said I love you, Kamokhelo, but I love it that you are together. Hopefully, we are continuing to be being together. It's very important to be together, guys, because when we are together, we get all the marks together. How can the domain of h... Can I see the solution? Oh, Kamokhelo, I want to see the solution. There it is, Kamokhelo. This was the solution. Okay. H of x is equal to f of x plus 2. Remember, the function itself that was there of f of x is this. This was f of x. So remember, we want the function of h of x. When f of x plus 2 minus 9, we want the equation of h of x. If f into x plus 2 minus 9. So what I've done is that in the place of x, in the function of f, I substituted x plus 2. So I replaced this x with x plus 2. There it is, x plus 2. Then follow it up with minus 2. There's the minus 2. There's the square. There's the square. Minus 9. Okay. But then of course I said plus 9 for the function f of x, then I subtract the 9 on the outside. Okay, where's the question? Here's the question. Write down the equation of h. So h is a new function. And what is the stipulated statement? If h of x is equal to f into x plus 2 minus 9. Write down the equation. So what we just did is we wrote down the equation. Okay, did a little bit of algebraic manipulation, of course, with the substitution, the addition and subtraction of like terms, and then the answer. All right, so that was the question, my Nosimilo Mazibu. So hopefully you understand and you can see what's happening there. Then after that, we were able to get to this place of negative x squared. Okay. So hopefully now we are together. We are together for sure. Hopefully we are. Okay. Right. Look at the next question, guys. How can the domain of h be restricted so that h inverse will be a function? Hopefully you guys saw what h of x is. It is a parabola. You're welcome, Nosmil. Yeah, the thing is you have a smilo, that's why I had to attend. How can the domain of h be restricted so that the inverse of h will be a function? You guys tell me. Remember, this is the function that we are talking about. It's a parabola. And I'm hoping you guys can remember from the notes and from the, you know, the concept of how do we, is the inverse normally of this function as it is it a function? That is the question. As it is. No, we know that the inverse of this, all right, as it stands, is not a function. It is a relation, okay, because it exhibits the property of 1 is to many, which is not a function, the inverse of the function. The inverse is not a function, it's a relation. So how do we then restrict, as it says, how can the domain of h be restricted so that the inverse will be a function? How can the domain of h be restricted? That's all they are asking for. How can we restrict it? What would we do, guys, to restrict so that we have a function in the inverse of it? What would we do? Anyone? Okay, 2 ways of restricting, guys. You just need to make sure you are able to just provide both. The part of it being not a function. Okay, I'm not going to use this example particularly. I'm going to use another one. Let's just say, guys, this is y is equal to x squared. Okay, we all agree this is y is equal to x squared. Okay, all right. Hey Theo, you just call me when I'm with your funny stuff. Just call me. So y is equal to x squared, right? This is the parabola function. Okay, concave up because the coefficient of x squared. Yes, I do. Link is in my bio. So this is y is equal to x squared. Coefficient of x squared is positive 1, so obviously smiling face. We have a turning point of 0, 0. So I hope that makes sense. If you were to express the function as its inverse, how do we do that? We would first obviously swap the x and the y. So in the place of x, y, we have x. In the place of x, we have y. Then we make y the subject. How? We take the square root on both sides. And then there's plus minus. So that means, therefore, y is equal to plus minus the square root of x. Okay, I hope that makes sense. Do you see that, right? Now, this function here this this here can be drawn in the following way. Okay, yeah, so I repeat once again. No, Kamogelo, this is not this. Remember, hey, now you guys are missing something here. This is a parabola, guys. This is a parabola. Y is equal to x squared. Your variable x is a base. Your exponent is a numerical value. It's a number. This is a variable. So be very careful. This is a parabola. There's no log that is involved in a parabola. It's only in your exponential function that you can express your inverse as a log function if you have an exponential function. Be careful, né? There's a difference. This is a parabola. So this parabola, as you see it, is y is equal to x squared. The inverse of this parabola is actually represented by this sketch. But what do you notice, guys? If you were to place a ruler, the vertical line test, what do you notice? This line cuts the graph at two places. If it cuts the graph at two places, it means we have a situation of 1 is to many. What do we mean by 1 is to many? It means one particular x value, because let's say if the x value here was 1, will give rise to many y values, right? Yeah, so this basically means that a 1 is to many is simply not a function. Okay, the only thing that we regard as a function is when a function we say is either 1 to 1 or we say many to 1. That's a function. When a function is 1 to 1, we say it's a function. Okay, and then if it's many to 1, we also say it's a function. For instance, this parabola, as you see it, y is equal to x squared, this is a function because this is a typical example of what? Of many to 1. Okay, very important, many to 1. Okay, but the minute it is like this, the inverse, y is equal to plus minus the square root of x, this here is a typical example of what? Of 1 is to many. It's not a function because the vertical line test, okay, it cuts at two places on the same vertical line, so that means it's not a function. This is a relation, so this is not a function. But in order for us to make this inverse to become a function, we have to restrict the original function. Okay, so if I was to take y is equal to x squared, let's say y is equal to x squared, and I say to you y is equal to x squared where x is greater than or equal to 0. Listen now, listen to me very carefully. Where x is greater than or equal to 0, let's go and resketch the graph. Where x is greater than or equal to 0, what do we mean by x is greater than or equal to 0? It means we are going to only draw this side of the parabola. We are not representing this side because we have restricted the graph of y is equal to x squared to becoming x greater than or equal to 0. Then listen to me. Now I take this function, restricted the domain to be x greater than or equal to 0. What does that mean? It means x is equal to 0, but it is also greater than 0. That's why you see it being represented this side as well. Listen to me and listen to me very well. Now, I take the same function, x is equal to y squared. I swap to get the inverse. Now I'm on my way to getting the inverse of the function with this restricted domain. X is equal to y squared, of course. Then what do? I take the square root on both sides, of course. Then I get x is equal to y square root. Y is equal to the square root of x, right? Yeah. And then that basically makes life very, very beautiful and easy. Okay? Therefore, y is equal to the square root of x. Okay? Yeah. Where x is greater than or equal to 0. Now listen to me and listen to me well. The inverse of this function would be represented by that particular arm. Yes, Kalogo, you first, but the very important thing first is to swap x and y. You must swap x and y first. So the y is equal to x squared, you first swap around. You see, y becomes x, and the x becomes y. Then you basically then make y the subject of the formula. Okay, because you would basically conclude now that the inverse of this function is the square root of x. And nakona, the positive square root of x, where x is greater than or equal to 0. Okay, so what you would then find is that this sketch, right? Typically, look at this. This particular restricted domain for this arm will have an inverse with this particular arm. So this and that. And if you see, when you've restricted the domain of the original function, that gives allowance for the inverse of the function to be expressed, yes, restricted in its domain. It allows the inverse to be expressed so that we can say now it is a what? It is a function, because this here is actually a 1:1 function. So we say the inverse here is a function because why? We restricted the domain of the original function so that we can allow the inverse to also be a function. And it's a 1:1 because it passes the vertical line test, because the vertical line test shows us that the function only cuts at one place. It does not cut twice in the same vertical line. So the inverse is a function. Also, it is symmetrical along the line y is equal to x, as it is supposed to be. You see, it is supposed to be symmetrical. The inverse is supposed to be symmetrical along the line y is equal to x. So this is one way of restricting the domain of the original function, but that's not the only way. We can also take y is equal to x squared and restrict it in this way. We say y is equal to x squared, we restrict it in this way. We say x is less than or equal to 0. So what does that mean when I sketch the function of y is equal to x squared? X less than or equal to 0 means I am seeing only this arm. As a result, what is the inverse? Of course, you do the same thing. You swap x and y, you take the square root, you express the answer. Then what do? We say that x is equal to, now listen very well, you would say y is equal to, when you finally write your answer, y is equal to, this time round you won't say positive square root of x, you are going to say negative of the square root of x, where x is what? Where x is greater than or equal to 0 for the inverse of that function, because the inverse would be this arm here, symmetrical, guys, along the line y is equal to x, but it would be this arm. If you go back to that function, we said that it is not to that parabola that was in this direction, which we said is not a function because it does not pass the vertical line test. Remember that this arm was symmetrical with this one. This arm is symmetrical with this one. But because now we have just the one arm, we say that the inverse of that function is actually a function because it is also 1:1. It passes the vertical line test because there's no second arm that's here that's making it so that it does not pass the vertical line test. It also passes the vertical line test. It is a 1:1 function. You see? So restricted in this domain, y is equal to negative. This is negative root x. Okay, whereas that other one was positive root x, this one. It was also symmetrical along the line y is equal to x. This one is also symmetrical along the line y is equal to x. So in other words, what am I saying to you? I am saying there are two ways to restrict your domain. You can either say x is greater than or equal to 0 for this function, or you can say x is less than or equal to 0. That is how you can restrict your domain in order for your inverse of the function, for your inverse to be acknowledged as a what? As a function. So that is why you can actually then say f inverse of x is equal to negative root x, where x is greater than or equal to 0. I hope now we understand, and at least there's a bit more solid understanding when it comes to this thing of how can the domain, if I go back to the question, how can the domain of H be restricted so that the inverse will be a function? Are we together now, guys? Are we together? Are we at least, yeah, we are, gaining something, because it's so important. Restricting the original function so that the inverse can become a function too. Okay, for the parabola. And yes, for a parabola, guys, there's no log involved. For a parabola, there's no log. It is only for a what, guys, where log is involved? It is only for your exponential function where log is involved. Okay, yeah, for your exponential function, let's differentiate between the two. For your parabola, the variable is a base, whereas your exponent is a numerical value. Okay, and Lacona, the variable is an x variable. Let's be careful about it. Let's be sure about that as well. It's an x variable, your base, and then your exponent is a numerical value. Please, let's differentiate between parabola and exponential. Let's not be confused about the two. We can't be thinking about this and then thinking log. No. Log is not even in our thoughts when we are thinking about parabola. Log is very far away. Yeah. Okay, let's look at the last. So this one, how can the domain of H be restricted? You can restrict it in two ways. You can either say x is greater than or equal to 0, or you can say x is less than or equal to 0, because remember, guys, this one was negative x squared. Okay, and negative x squared, what are you expecting? You're expecting a function that is concave down like this. It's also touching the origin, but it's concave down like this. Okay, yeah. So then there are two ways in which you can restrict the domain of the original function. As you can see the question there, how can the domain of H, what is H? H is this, the original function, negative x squared. How do you restrict him so that it gives room for the inverse, so that it can be acknowledged as a function? So two ways. This is one of your answers. You can say x greater than or equal to 0. You can restrict it in this way, or you can say x less than or equal to 0. Okay, you include, guys, the 0 because this turning point is at the origin. Are we together? Hey, I hope we are together here, guys. Okay, so yeah, that's how the domain can be restricted. Okay, cool 8, close. Yeah, I hope we are cool, guys. Cool. 1.1.6. Show. Now this here, you see these words in maths when they say show or prove. Yeah, it's so important. Take the left hand side, deal with it on its own. Take the right hand side, deal with it on its own, and then see when you put them together if they are the same. Yeah, because here they're saying g of x plus half. Where is g? There is g. Is it? Show that g of x plus half is equal to the square root of 3 into g of x. Okay. Yeah. G of x plus half is equal to the square root of 3 g of x. It's a level 3 question, as they're saying, and they're saying it's for 3 beautiful marks. I mean, not for 3 beautiful. It's a level 3, it's 2 beautiful marks. Okay, let me give you some time to do this. Give you some time. You can do it. You can do it. Okay, so I hope you guys have spent some time. At least you will remember most that we did find the b value. We did find it that it was 3. You remember that? So we know what g of x, the function. We know that the function of g of x, right, is equal to 3 to the power x. We know that. So now they are giving us show algebraically that g of x plus half, let's see, g of x plus half is equal to the square root of g of 3 g of x. Okay. And really and truly, if they are saying show, okay, that means we are actually required to prove that this is the case. So what I would do personally is I would take the left hand side, which is g of x plus half, Well, we know what g of x is. That means in the place of where of what of x, we are substituting x plus half here on 3. So we're gonna say 3 to the power x plus half. Very important. That's our left hand side. Okay, and then that means 3 to the power x can be written as 3 to the power x times 3 to the power half. That's simply using our exponential laws, right? And then from there, we know that we can write 3 to the power x as 3. We can write 3.5 as the square root of 3. And since multiplication is commutative, it means we can say the square root of 3 times the 3 to the power x, simply put. Okay, if we go to the right hand side, which is that, we know this is the square root of 3. Now g, it's multiplied with g of x, so that means in the place of g of x, we are going to write what? G of x is equal to 3 to the power x, so it's times 3 to the power x. Can't you see, guys, that our left hand side is that, our right hand side is that? I think we are done. Left hand side is equal to right hand side. So in other words, g of x plus half is really equal to 3 times g of x. Done and dusted. What more do they want from us? Could they want anything more than that? Now imagine exponential laws are forgotten. You see? Yeah, because all of this is the one that's playing a role now. You see, I used the reverse. A to the power m plus n is equal to a to the power m times a to the power n. I use the reverse of this law to split these two. Okay, and then look at that. This a to the power m over n is equal to a to the power what? A to the power what? We can say the square root of what? The nth root. You see, these are things that we forget, guys. These are simple things that we forget. And I'm telling you, basics. The basics of every single topic are the one thing that we all have to make sure that we master. If we forget the basics, I'm telling you guys, simple things that we're supposed to easily get will become problematic. We are going to lose marks there and there unnecessarily. Why? Because we have failed to ensure that all the conceptual knowledge that we need as we prepare for the exams is actually solid. I ask and I beg all of you, please guys, make sure that the basics of all the topics, you make sure that you understand. Things like board mass, guys, board mass, you know, hey. Basic things like that. I'm telling you, there are things that they are the ones that lead to your mark loss, you know. So please make sure that the basics are sorted, you know, the laws, you see. So I use these to basically get to my answer. It was nothing special, nothing phenomenal, nothing out of the ordinary, just basics, basic stuff. Okay, I hope you are following here and you are with me here. I really hope so. Okay, because if that is the case, then we are going to be good. We are going to be good. All right. Yeah. Please, guys. Please. Ensure that such is taken care of. Yeah. Guys, I'm going to have to love and leave you now. Okay, I will pick up on this because, like I said, I'll be gradually doing these functions and just unpacking things slowly but surely. But please remember, I am simply trying to be a catalyst behind your preparation towards the exams. So don't wait for me to go live. Use whatever you may have heard me share today and use that to catalyze your own preparation. All right, and yeah, if you have questions during the course of the day, you're busy practicing and you're like, hey, I'm stuck here, please ask, send me messages and so forth. If you're doing work and you're unsure about your attempt and you just want me to check it, take a picture and send. It's, inbox me type thing. Yeah, so this is another question that we'll definitely look at when we congregate and meet again. Okay, it has to do obviously with exponents, and what I like about this question, of course, is the fact that it has exponents, right? Exponential function 2 to the power x plus 2, but also at the same time it has a log function, f of x is equal to log half x. Okay, so I think what I'm actually going to do just before I leave the live, I'm going to do this question, all right, and then I'll leave you after that. Look at this. The sketch below shows the graph of g of x is equal to 2 to the power x plus 2. Okay, f of x is equal to log x base half. Graph f and the asymptote of g. Graph f, there's graph f, and the asymptote of g, there's the asymptote of g, intersect at b, and we are given the x coordinate of that where they intersect. Okay, we're given the x coordinate, half and 2. Write down the coordinates of who? Of a and the x-intercept of f. Write down the coordinates of who? Of a. And a is the x-intercept, guys. Write down the coordinates of a and the x-intercept of f. Where's f? Or write down the coordinates of a, the x-intercept of f. So a is the x-intercept of f. Where's the function of f? There it is. F of x is equal to log x base half. So let's go. F of x is equal to log x base half. We are asked to write down the x-intercept of f. This is where we let y be 0. F of x is y. Y is equal to log half x. In the place x-intercept, we let y be 0. So 0 is equal to log. Then this half, if we want to solve for x, the half goes and kicks the 0 and catches it. Very important. The half, which is the base, goes and kicks the 0. It acts as the base on the other side and carries the 0, becomes its exponent, and then the x is left isolated. Okay, that's how I think about it, So to change log back to exponential form, the half kicks the 0 and then carries it, sort of like carries it in the air, holds it up, and then the x is isolated, the log disappears. What's half to the power 0? It's 1. So x is equal to who? To 1. What are the coordinates of a when y is 0, x is 1? So these are the coordinates of a. Okay. All right. Any real questions here? Log is the function of f. A passes or touches the function of f. What is it? It is the x-intercept of f. A is the x-intercept of f. Okay. A is the x-intercept of f. Let's go back. Right, let's just go back there to the statement. The sketch below shows the graphs of g. Where's g? Here is g. 2 to the power x plus 2. And f of x. Where's f? Here is f. Log x base half. Here it is. Graph f. Where's graph f? Here is graph f. And the asymptote of g. This g, the asymptote of g is here. So graph f, which is this, and the asymptote of g, which is there, intersect. So this function of f and this asymptote, they touch or meet or intersect. They cross each other at b. There's b. And we are told the coordinates of b are half. We are told the x coordinate of b, but we're not told the y coordinate of b. So we don't know what the y coordinate is. Okay, we are given the variable q. Okay, and it is in line with the asymptote. Of course, it makes sense, of the function, because the q value speaks of the horizontal asymptote, okay, which is also the y coordinate of b because it lies on the asymptote. Anyways, that's fine. Write down the coordinates. They want us to write down the coordinates of who? Of a. What is a? The x-intercept of f. What is the x-intercept? Where the graph cuts the x-axis, where this function of f will cut the x-axis. X-intercept, that's where we let y be equal to 0. X-intercept is where we let y be equal to 0. Okay, so in the place of y, we write 0. 0 is equal to the function of f log x base half. Then after that, we solve for x. How do we solve for x with log? We take the base of log, kicks the 0, and then that 0 becomes an exponent, so half to the power 0 is 1. X becomes the subject, log disappears, so x is equal to half to the power 0. Half to the power 0 is 1, so x is equal to 1. That means when y is equal to 0, x is equal to 1. That is the coordinates of a, 1 and 0. Okay, are we together now? Ngwa, do, ns. Ngwa, do, ns. You said repeat the question, please. I repeated the question and I went through how we answered the question. Are you fine now? Ngwa, do, ns. Amanda, H. Sunday and Clove. Kamukher, Mabon. Are we good? Can I go on to the next question? It's calling us. Question 2.1 is answered. Now we need to go to question 2. Okay, sir. Yes, Kamukher. Are you? Is that a sir with exclamation, question, or affirmation? Exclamation for affirmation. Okay. Okay, no problem. Then next question. Next question. Determine the domain of f. There is f. It is an exponential function and it seems like it has an asymptote here. This vertical line is where this graph is not crossing. It's coming close to this line but not ever touching it. Remember, this arrow is just an arrow, but the function itself is never going to touch this line. It's never going to go beyond this line. Okay, so that means if we're going to write down the domain, determine the domain of who? Of f. It means that from left to right, where is the function defined? From left to right. We can see that f is not going to exist on this side of the function. Of the x-axis. So, but at 0 as well, it's not going to exist because it is the asymptote. But beyond 0, it means the function does exist. So that means when x is greater than 0, the function is existing. So I would say that the domain is x greater than 0. Or we could say x is an element of 0 to infinity. It depends on who's writing. If you write your answer this way, you're 100% correct. X greater than 0, that's good. Or you can say x is an element, open brackets. Why are we saying open brackets? Because we're not including the 0. The function is not defined at the 0. Okay, clearly so. So we say x is an element of 0 to infinity, open brackets. Okay, you can write your answer this way, we can write your answer that way. Someone may be sitting there and asking themselves, so how did you know that the function does not go beyond this line? It's because, remember, log is the inverse function here in this situation. This is the inverse function. And the inverse function, obviously, has an asymptote that is vertical, not horizontal in this situation, because it's the inverse function. So that's why I can clearly see that this here, this parabola, not this parabola, this exponential function is not going to go beyond the y-axis. Okay, in actual fact, it is a boundary line, okay, because it's the inverse. So basically we say x is greater than 0 is the inverse of that, is the domain of this function here. So yeah, moving right along to 2.3. Determine the equation of the inverse of f in the form y is equal to. The inverse. We need the equation of the inverse. Okay, so the log form here is what we have. So we want the exponential form. That would be the inverse of the log form. So we need to convert this log form into the exponential form, because that would be the equation of the inverse of this function. Okay, so if you are given the log form to express the inverse, then you know that you are going to be converting this log form to your exponential function into exponential form. But if you are given exponential form and you want to convert it to inverse, then obviously the inverse would be the log form. So now in this case, we are given the log form. We want to rewrite this into the inverse form, the exponential form. So how do we determine the equation of f inverse in the form y is equal to, for 2 marks, of the log form? Well, we do what we know what we should do. F of x is equal to log. Let's first write down the function. F of x is equal to log x base half. Then obviously say y is equal to log half, then the x, of course, we know, right? Then we swap first. Let's first swap. We know most. It's always the case. We have to first always swap. So what do we mean by swapping? We mean that the y becomes x and the x becomes y. Very important to first swap. I laugh at my kids when they say, no, we must swipe. I always think of like swiping my card at the bank. It's like, you must swipe, sir, you must swipe. And they say it with such confidence with swiping. And I'm like, guys, I don't know, this pronunciation stuff of yours, it's really killing me, but it's swap. We swap, guys. We swap x, y becomes x and x becomes y. Then after that, we play that game where x, what does it do? X will kick, half will kick the x. It's like today, I'm sure when you watch the rugby, I don't know if you guys watch rugby anyways, but yeah, sorry, not today. It's a new day today. It's Sunday, but I mean, just yesterday, the Mapokopoko were playing against Argentina, and hey guys, I've never seen our fly half kick so well. Fly half was man of the match. Like, he was doing phenomenal stuff. Like, the kicking was on point. And everything. So it's like our fly half is the fly half. What the fly half does, he kicks the ball, it goes up the ball. So you have a half to the power x. You see, they kick, it goes up. Then we isolate. Who gets left behind? Mr. Y. Log falls away. So the equation, there it is. Okay, y is equal to half to the power x. This is the inverse. So now you can say the inverse is half to the power x. But you remember they said there they want us to write the equation in the form. So please take note and be very careful, be mindful. They saying here, determine the equation of the inverse in the form. So when they say in the form, you must make sure your final answer is in the form where the subject is y equal to and then the actual expression. Okay, so there it is. Y is equal to half to the power x. Okay, are we good? I think that was nice, Jay. Very nice. Okay, so once again, what do? We take the function, we write, f of x, we change the functional notation to y is equal to, we swap, not swipe guys, we swap x and y. Then after that, we just play the Amapoko game, fly half stuff. Okay, half kicks the x, becomes the exponent, y becomes isolated, y is equal to half to the power x. Then that's the equation basically, or the formula, the function, with the subject y. Yeah, we swipe. don't swipe, please guys, swap, please. Okay, clear. Okay, let's go to the next one. Now they are saying, sketch the graph of the inverse. Indicate on your graph the intercepts with the axes and the coordinates of one other point on the graph. Sketch the graph of the inverse. Indicate on your graph the intercepts with the axis and the coordinates of one other point on the graph. So now they want you to sketch basically this function. Okay, and clearly guys, you can see that there's an asymptote there, which is basically going to be, you see, plus 2 is 0. Okay, so that means you're going to have your x-axis as your horizontal asymptote. That's very important, because you must always know the asymptote before you sketch an exponential function. Then, to be honest guys, I really prefer that whenever we are sketching a function like this, then we simply use -1 or 0 and 1 if there's no sort of like directive as such. So I tend to really like using that. We know our x values are just going to substitute -1, 0 and 1, so that we just have an idea as to where the function will be. So in my head already, I know that a is +1, b is half. If you remember when we were talking about exponential functions, when a is greater than 0, it means the function will be above the asymptote. So the 1 is outside there. You can't see it, but it's there. The exponent, the base of the variable is actually between 0 and 1. So when you have this combination, it's very clear that the function will be a decreasing one like this. So in my head, I already know the shape of the function. I am expecting something like this, because from my conceptual knowledge of the types of functions that I have, when a is greater than 0 and b, the base of the variable x, is greater than 1, it's an increasing function. When a is greater than 0 and b is between 0 and 1, then it's a decreasing function like this. Of course, for both a greater than 0, we know the function is above the asymptote. Okay, then when a is less than 0 and b is greater than 1, it's below the asymptote but decreasing. A less than 0, b between 0 and 1, it's below the asymptote but increasing. So in my head, I am already knowing in my head the kind of function I will see prevail as I sketch. So there's no ways I'm going to make a mistake when sketching the function. No ways in nothing. So I substitute -1 there. You can quickly use your calculator. You can use your table function as well and just put in -1, 0 and 1 and just check what you get as your corresponding values, and then you can sketch those on your function. So I know, for instance, -1 is going to be here, 0 is going to be there, 1 is going to be there, and then I just take -1, I substitute, yeah, and then obviously -1 will give me 2. When x is -1, y is 2. I substitute 0, I get 1. I substitute 1, I get half. So let's just see. And if you remember, these people said in the question that when you sketch the graph, indicate on your graph the intercepts. Okay, the intercepts with the axis and the coordinates of one other point on the graph. So I'm going to give them the courtesy of at least providing a point, -1 and 2, which is going to be this point there. Intercept that 1, okay, 0 and 1 definitely will indicate that one, okay. And I think I've given them enough info, and then I write the equation of the asymptote for my horizontal x-axis, that it's y is equal to 0, okay. Obviously you'd use your ruler and you'd sketch appropriately, but I mean, I hope I proved, or at least proved the point. You see, it's a decreasing straight line above the asymptote as suggested by the conditions on my a and my b value that are there on the equation of the function. And then this does not ever touch this horizontal asymptote y is equal, doesn't touch it at all. So that's my y-axis, that's my x-axis, and then that's that, guys. That's my sketch. You would use your pencil and you'd make sure that your sketch is 100% flowing, but you would obviously make it neat and tidy and nice so that you get your 3 marks for 1, your shape, 2, your x-intercept and your one other point, and then 3, labeling your asymptote. So your shape, the right shape, your x-intercept and your other point that they said you should indicate, and then your asymptote, labeling your asymptote and making sure that you show them that this is a point, a line where the function does not touch y is equal to 0. Okay. Any other questions? Okay, now they are asking, determine the equation of the asymptotes of G. Determine the equation of the asymptote of G. Remember, guys, that they said that B, okay, is a point that lies on this log function. Now what we want is we want the equation of the asymptote of G, and in order to get the equation of the asymptote of G, we need the y-coordinate of this particular point, point B. So at least we know that this point lies on this line, which is the log function. So let's go there to the log function. Y is equal to log x half. Now we know that B is half and Q. So to get the Q value, that's the Y. Q is equal to, let's go, log half. Okay. Then we can say half to the power Q is equal to half. You see? Yeah, because we're playing the rugby game. Half kicks the Q, carries. Then we have half to the power Q is equal to half. Now obviously that Q, that half, is raised to the power 1. We know when the bases are the same in exponents, what do? We drop the base, we equate the exponents. So that means our Q value is equal to 1. What is the equation of the horizontal asymptote? It's y is equal to 1. Okay, y is equal to 1 because our Q value, meaning our Q value here, is half and 1. So y is equal to 1. Very good, Kamukhail. I think you actually beat me to the answer. You beat me to the answer. determine the equation of the asymptote. Please, when you write the equation, y is equal to 1. Very good, Kamohelo. Kamohelo is like, this girl is on fire. Mama Bolo, yeah, you're on fire, eh? Last question for today, guys. And please, you must practice so that you get better and better in functions. Describe in words the transformation of G. Where is G? G to what? To F. Describe in words the transformation. That's for 2 marks, level 3 question. Okay, describe the transformation of G, or to the inverse of F. Not to F, but to the inverse of F. Now let's just go ahead and write down the equation of G first. G of x is equal to 2 to the power x plus 1. Whereas the inverse of f we discovered is actually equal to what? We wrote down the equation. It's half to the power x. So now they are asking us to describe the transformation. How do we move from here to there? Let me check. What will my people say? Let me listen to you guys. You let me know. What do you think in the comment section? Describe the transformation. Talk to me. I'm listening. This is the last question. I'm going to give you a good 5 minutes. Well, not 5 minutes. 3 minutes, 2 minutes. No, 2 minutes at least. Think about it. And then let me know in the comment section what you think. The question says, describe in words the transformation of G to F. So that means you need to describe how do we move from here to there. What would we have to do to get G to become F? What do you do to G to get it to become the inverse? No. Baby J's. No. They are saying describe how do you transform G so that it becomes F? Okay, transformation has to do with the changes that G would have to undergo. This is like me saying to you, baby J's, how do we convert a sinner like you to become a saint? How do we change or transform a sinner like you to become a saint? A saint that can one day become a candidate for heaven and enter there. That would be like that. That's like seeing, that's basically like an example of what I'm trying to say you ought to be describing. We need to so it's like you seeing a sinner. Here's the sinner, but now all of a sudden this sinner is a saint. What happened to this sinner to become a saint? So what happened to G of x to have now what we have F? How did it happen? What changes took place? Right? Describe the changes. Okay. So when you look at this and look at that, look at the to the power x. There's to the power x. Look at the 2. Hypo. Here there's half. Habo. Katukun. What happened? Look at plus 1. Here there is no plus 1. There's nothing. What happened? Boo. Speak to me. Amanda, I think we transformed by decreasing it on the y values. Okay, Amanda, you are heading somewhere. I like what you are saying. Decreasing the y values with the value of 1. But what is that? What is that transformation actually called? What happened to this graph? What is that? When you decrease by 1, what is that? Physically, what did we do to the graph? If you are saying we decreased it on the y values with the value of 1, what did we physically do to g of x? What did we do to it? Yeah, but you are on the money. But now we need to have descriptive terms. Because this thing is saying, describing words, the what? The transformation. The transformation. Kamogelo is saying the graph shifted 1 unit to the left. Be careful, Kamogelo. Be careful, Kamogelo. Kamogelo is saying 1 unit to the left. 1 unit to the left. Okay. Kamogelo, you are not, not to the left. Okay. Yeah. Because with this here, what is it affecting? Is it affecting left and right movement, or is it affecting up and down movement? You see, that's where you should see Kamogelo. Left or right, up or down, okay. This particular parameter, the parameter q, okay, y is equal to ab to the power x plus p plus q. This q, what is it in the transformation? We say this is vertical shift. When q is greater than 0, up movement. Q less than 0, down movement. So let's be very careful. Q has to do with transformation, vertical shift. Okay. So if we want to say down, we are subtracting something. If we are saying up, we are adding something. Okay. Then here, P is the one that affects left or right. And P greater than 0 to the left. P less than 0 to the right. So this is horizontal shift. Okay. So these are the words or the terminology that we use when we are talking about the transformation. Okay, the P parameter affects transformation horizontally. P greater than 0 to the left. P less than 0 to the right. The Q value, it has to do with the vertical shift or translation. Q greater than 0, up. Q less than 0, down. Guys, this applies to all the functions. Okay, all the functions. I'm going to come here now. Let's come back to the notes, because it means there's one last thing I need to touch. The hyperbola, this Q has to do with vertical shift. Okay, and guys, it's the same thing. Q greater than 0, up. Q less than 0, down. This P has to do with horizontal shift. P greater than 0 to the left. P less than 0 to the right. Counterintuitive. The P value is the one that is counterintuitive. It's against your natural grain of thought. Do you hear what I'm saying with P? I'm saying with P, when P is greater than 0, you would think we are going to the right, but no, P greater than 0 means to the left. It's against what you're thinking. That's the P. P is very interesting, the horizontal shift, the horizontal movement of the graph. It's the same thing here. Q, up and down. P, same thing, guys. P greater than 0, to the left. P less than 0, to the right. Same thing for the parabola, hyperbola, exponential. P and Q play the same role. It's the same thing with your trigonometric graphs. Get that and be safe and sane. Don't confuse the two. I'm coming back now to the same question. There's one thing I have not really spoken about, and I'm sure when I speak about it here, you will see. So do you want me, guys, do you want me to tell you how G transformed to become F? Do you want me to show you what happened? Can I tell you? Are you ready for what I have to say? Okay. Yeah. Okay. Let's first start here. Please tell us. Please show us. Kamogelo is so funny. Please tell us. Please show us. Here, +1. Now we have what's happening? From +1 to having what? 0. What happened? It means we subtracted 1, right? Now, if you subtract 1, what happened to G? G of X shifted down by what? By 1 unit. What happened? G did what? If it was +1 and we subtract 1, we get that 0 that basically is there for this function. So what happened to G? G shifted down by 1 unit. That's the first thing that happened. Are we together with that one? I hope we are not. No, that's a transformation. The graph, you can say shifted down, or you can say it moved down by 1 unit, or you could say it translated down by 1 unit. These are different words that I'm using. Shifted down, moved down, translated downwards by 1 unit. So this is what we mean by transformation. What happened to G? G is the one that shifted down by 1 unit. From +1 to 0, we subtracted 1. That's a shift down. That's a transformation one. That's not the only thing that happened. Now you are going to check here. Hypo, there's 2 here. Katuking, half. What happened? Okay, guys, I hope you can see that from 2 to half, something happened here with the exponent of x. From 2 having a positive 1x to half, that means 2 got multiplied with a -1. Now some of you are going to be like, Aibo, really? Yes. So that means x changed from positive to negative, because you know fully well that 2 to the power -1 is equal to a half to the power x. 2 to the power. Now we are back to exponents, guys. We are back to this idea of exponents. Hey, and people don't know their basics. Hey, Kantuking. Hey, Bana. And then we cry. Hey, guys. Hey. We must pass. We must pass, guys. We must pass. Okay. So when x changes sign, okay, in other words, when there's a change in x, you see x, the coefficient of x was positive. Now all of a sudden the coefficient of x, to get from 2 to half, it means that when you don't see it, but remember, half is the same thing as 2 to the power -1. You will see it if you know your exponential laws and your definitions, that half is the same thing as 2 to the power -1. So there was a change in the coefficient of x. In other words, a change in x. What does that mean? It means G is reflected along the y-axis. What? G is reflected along the y-axis. So say, what are you saying to us? Say is saying to you, change in the sign of x means a reflection in the other variable, not x, but the opposite of x, which is y. Change in who? In x means a reflection in the other variable. Change in y means a reflection in the other variable x. Are we together, guys? Ngwanes, are you with me? So this is the second transformation that happened. G reflected in the y-axis, not the x-axis. Remember, who's changing x, but who's reflecting y. So these are the two things that happened, that G transformed to F. Hey, Ngwanes, listen to me and listen to me and listen to me well. So I hope you are with me. And guys, this is where I stop for today. Thank you so much. I hope you learned and you gained, because what's important for me is for you to learn and gain. And then once you've gained, you must go and practice some more. You must daily do something that will be an investment towards your writing of the end of the year exam, so that you can internalize and master what you've learned. If you don't do that, then if you put a break and a gap and you wait and you forget again and you want to be retaught again, then I don't know what more you want. Then you are basically setting yourself up for a disaster. Please, guys, I believe that we have grasped, we have learned. Now we need to just go and practice more and more. Tomorrow I will come back, we will do more. As you can see, we have some hyperbola questions that are coming up, but like I said, you don't have to wait for me to internalize, master, and understand these things. Me, I'll just come and support what is already happening with you. There are more questions that are lined up, as you can see on this document and this page. More and more, and there's more things to be learned. So thank you so much, guys. I'm going to hold it right there. I can't show vertical horizontal shape because, guys, I am working this morning, so I have to leave now. If I don't sleep, I won't get enough rest. Then I'll be crying and I'll be blaming you. Okay, so what I'm going to do is I'm going to download this video, upload it onto my YouTube channel, as I've already also uploaded the video that I did of the live lesson we did yesterday, so that you guys, if you want to go rewatch, can go and rewatch. The quality may not be as great because it's just simply the same quality live as you see it right now. I'm moving all about, sometimes saying a lot of things that are not even math related, so that people can grasp and explaining things over and over again. But guys, please, you must use these fast forward things that are there on YouTube. You must times 2, so that the thing goes fast if you feel like it's going too slow, and move on to where you feel you needed to confirm certain things that you may have missed here. But thank you again. Have a beautiful, beautiful morning. Be as beautiful as ever, and God bless you as you prepare. I pray God's mightiest of blessings upon your life, upon your future, and upon your future endeavors. May God continue to just help you grasp, keep, retain, maintain the knowledge that you've gained today, and may He be with you. Do not be discouraged, do not fear, press on. Your dream is valid, black child. Yeah, love you. Have a great one.